All right, anybody have any questions? All right, hearing none, and it looks like it's 1 o'clock now. Today what we're going to do is we're going to cover two things. Basically, it's all the same kind of stuff. It's section 3.6 out of our normal book, and then some of those handouts that are kind of tied throughout the rest of the session. There's like 3 or 4 of them, and this is one of them. It's section 3.3, real zeros of polynomials. It's out of the other book, and it should be in your Moodle. You can download it and look at it and read it as well. And it's just got a couple extra things in it that's not in 3.6. Plus, it has also some good example exercises in the back of that section that are good to practice. They're a little more difficult than the ones in our book, so they're more kind of realistic type problems, and they also have all the answers, so you don't have to worry about as far as not knowing what the answer is. They actually have the answers in there too. So both of these are good sections to kind of tie it all together. And with speaking about that, I've kind of moved things around to make it easier as far as solving problems by learning different theorems and algorithms earlier than it shows in the book. So not everything is going to be kind of in the order the book shows. It's going to be a little bit of 3.6, a little bit of 3.3, back and forth until it kind of hopefully gets it so it makes it so it's easier to solve things. All right, so what we're going to do is we're going to evaluate polynomials using the remainder theorem, and that's going to be done instead of substituting values and simplifying. So say we had f of x equals 3x squared minus 4x plus 5. Instead of plugging in x equals 2 into all the things, what we're going to do is we're going to use the remainder theorem to help us with that. And how that works is, so if we have some polynomial f of x, again, doesn't matter what one it is, and if we divide by x minus k, so k is going to be our value we're looking at to see if it's a 0, and or it's a number, like if they say what is f of 2, then k is going to be 2. Then the remainder is the value for f of k. So then f of 2 would be whatever that synthetic division would be. And so what we're looking at here is, so they give us f of k for any given polynomial using the remainder theorem. So if we have f of 2 and we want to find that for this exact polynomial, all we're going to do is we're going to do synthetic division. And if I turn my pen around the other way, I'll get the thing. And so what we're going to do is we're just going to take 2 and do a synthetic division for this. And notice we don't have a 3, so there's going to be a 0x to the third, and there's not an x, so there's going to be a 0x. And so we have a 1, then a 0, then a negative 9, and then another 0, and then the 14. And then whatever value we get out here, that's what f of 2 is. So if we had plugged in 2, whatever we get out here is what's going to be the case. So we do our synthetic division. That's 1. So then 2 times 1 is 2. 2 plus 0 is 2. 2 times 2 is 4. Minus 9 plus 4 is going to be a negative 5. That's going to give us a negative 10. Add those together, that gives us a negative 10. Now that gives us a negative 20. And then minus 20 plus 14 is going to give us a negative 6. So that says that f of 2 is going to be equal to a negative 6. And we would get the same thing as if we plugged it in here, we'd get negative 6 for answer, but we didn't have to do it. And this really works nicely as far as it's quick, it's not too hard, and you don't even really need a calculator to do it. So, sometimes when you're taking 2 to the 4th or maybe 2 to the 8th or something like that, it's going to be a little more difficult than doing this by hand, and it's a lot easier. And a lot of these, I'm only going to give one example, then I'm going to make another video after this and give more examples, some of them more difficult. That way you kind of get an idea of what's going to go on for those. All right, so the next thing we're going to look at is called the factor theorem. So if k is a 0 of f of x, if and only if x minus k is a factor of f of x. And so basically what we have to have is we have to have that remainder to be 0 in a synthetic division. So what we're going to do is we're going to be given some polynomial, some f of x. They're going to give us a factor, or they say, is this a factor? And then what we're going to do is we're going to say, okay, well, that k is equal to the 1, and we'll do the synthetic division. And if it works out, that'll give us the factor, plus it'll give us what's the other factor of this, and then we can go from there and see what we have. So if this is the 1, we have a 3, 2, 1, 0, so we have all of them, so that's a 2, -9, 13, -6. So we bring down our first, which is a 2. 1 times 2 is 2. -9 plus 2 is -7. Times 1 is a -7. 13 minus 7 is 6. 1 times that's 6. And when we add that, that's 0. So that means that is a factor. And what's left over then is this is going to be the x squared term, this is the x term, and then this is the number. And so what we have then are x minus 1 times, then we have a 2x squared minus 7x plus 6. Now the question is, can we actually factor the trinomial without doing any more division? So we could do another synthetic division, and we'll learn how to decide what numbers to try in a little while. But right now, can we factor that? Well, x minus x, well, here, let's erase that. Maybe. So we have x minus 1, and then that's going to be a 2x and an x. And then 6 is either going to be 2 and 3 or 1 and 6. If we try the 3s, the 3 has to go here, the 2 will have to go here. We want a -7. Both of them have to be negative, actually, so that should work. -3, -4. And so all real zeros, so we set each of those equal to 0, so we get x equals 1. We get x equals, here are 3 halves, and here x equals 2. So those are the 3 zeros for this trinomial, 2x cubed minus 9x squared plus 13x minus 6. And that's by taking the first factor and dividing it, and then the second one we actually just had to factor into the two terms and then set each one of those equal to 0 using the zero product rule, and we get our 3 zeros. Okay. All right, so all real zeros can be actually found within an interval. So, if we're going along, we might not know what interval to use, but there's actually a theorem that will tell us you should find everything within, -5 to +5 or something like that. And it all is based on Cauchy's bound theorem. And so basically we're going to have, some function, some polynomial function, and it's going to be of degree n, where n has to be greater than or equal to 1, so it has to at least have one term of x. And then we're going to let m be the largest of the numbers. And what we're going to do is we're going to take each of the coefficients and divide by our leading term. So we're going to take the absolute values of them so we don't have to worry about signs. And so we'll take a0 divided by an. We'll take the a1 divided by an, the a2 over an, all the way up to the an minus 1 over an. And we'll look and see which one of those divisions, whatever they are, is going to be the largest, and that's going to give us what m is. And then all real zeros for this function or this polynomial are going to lie in an interval from minus m plus 1 to m plus 1. Okay, and so this is just going to tell us where are they going to lie. So if we have something and maybe we factored it and we found some possible zeros and one of the zeros is beyond that, we don't even have to test it because we already know that it's going to be within this range. And so this is just kind of help you so you don't try something beyond the range. And so for this one, what we're going to do is we're just going to take each of our coefficients here, the 32, the 40, the 12, the 2, and we're going to put it all over the 1. And so if we start with a0, that's going to be 32 over 1. Then we'll have a 40 over 1. We'll have a 12 over 1. We'll have a 2 over 1. And so those are going to be all of these values. We basically have taken the absolute value of each of them, and now we divide them, and so basically it's just the number in the numerator. So 32, 40, 12, and 2. Which one is the largest? Well, this one is the largest, so m is equal to 40. So our interval is going to be between a negative 40 plus 1, which is 41, to a maximum of, not a 40, a 41, to a maximum of 41. And so we know that all of our zeros should be within this region here, okay? And a lot of times what happens is, they're really close, they're like 40 or something like that. And that's why we always add one just in case it's 40 and a half or something like that. And so that'll tell us where our zeros will be found, what region they're in, and it's going to help us kind of simplify things as we go. And so while as its own self, it really doesn't do anything, when you start adding it together with a whole bunch of other things, that's where it really starts coming into play. Now, like I said, it tells you where the zeros are going to be, but what are the possible zeros? Well, the possible zeros we can get from something called the Rational Zero Theorem. And so again, what we're going to have is we're going to have some function f of x, and it's, again, I'm not going to read all that out. And again, it's going to have a degree of n with n having to be greater than or equal to 1. And then each of our coefficients, basically, we're saying are going to be integers. And so if we have r as a rational zero of this function, then r is of the form plus or minus p over q, where p is going to be some factor of the constant term a0. So what we're going to do is we're going to have to factor this into all the different factors. And then q is a factor of the leading coefficient. So then we're also going to have to factor this. And we're going to have to consider all of the a0 factors divided by all of the a sub n factors, and then plus or minus of those. And that will give us a total list of possible zeros. Now, not all of them are going to be zeros, of course, but that's going to give us a possible list. And so then if we didn't have some things that we're going to learn about in the future, what we'd have to do is we'd have to go and exhaust that list doing synthetic division and to find our actual zeros. So we'd do the synthetic division. If we got the last little box was a 0, then we know we have a factor. Then from there we could go and do the whole list again and see if any of them divide out again. So again, what we're going to do is we're going to use all these plus or minus q's with synthetic division to find our zeros. Now, we have something also called the upper and lower bounds. And so what we're going to see is we're going to let f of x be a polynomial. So again, it's going to look something like that. So I didn't want to write it out all again. And it's going to be degree n greater than or equal to 1. Then if we do that synthetic division with whatever p's over q's we have, and we're going to use the c greater than 0. So we're going to use some p over q that's greater than 0. Then the final line of the division, if it has all the same signs, then we know we've got the upper bound for the real zeros. So whatever that c is going to be the upper bound. So nothing else is going to be greater. So if we work our way through and we hit one that's like maybe 4, and we get all positives or all negatives in that last line of the division, then what's going to happen is we know that's the biggest one it is, and we need to start going to the negatives after that probably, because there's not going to be any real zeros greater than that. Now, if we, on the other hand, come over here and we plug in a c that's going to be less than 0, and then at bottom line of the synthetic division has alternating signs, so plus, minus, then what we found is the lowest bound. So then c is the lowest bound for all the zeros, and there's going to be no real zero less than that c. And so if we've done that, we got all the way to the bottom, so there won't be anything less than that. And so this is going to help us when we get a huge list of maybe 20 or 30 p over q's that we have to start dividing. If we work through them and we get to a certain point and we either have all the same signs, we know that's the largest, or we have all alternating signs, that's going to be the smallest, and we don't have to go further each direction. Now note, if we get a 0 within the final line, that can take a place of a plus or a minus depending on what we want it to be. So if we have all pluses and then we have a 0 right in the middle, we'll call that a plus as well. Or if we have plus, minus, 0, and then the next one makes it so it would be alternating, we'll make that 0 a plus then. So it all depends on what we need it to be and how it's going to work. We can either make it a plus or a minus. So what we're going to do is we're just going to kind of use those, two or three things, and we're going to actually start looking for possible lists of rational zeros. Then we'll start making a possible list and kind of simplifying them, and then we'll actually find them. All right, so to find them, we need, again, the p's over the q's, and it's going to be plus or minus. And so we need all the factors of the a0, and this is going to be all the factors of our an. So our a0 is 32. So basically, I'm just going to start going down. Well, 2, and that's going to give us 16. And then that's going to give us 2 and 8. And that's going to give us 2 and 4. That's going to give us 2 and 2. And because we also want to have 1 in there, we're going to put 1 as one of the factors. And so basically, 1, 2, 4, 8, 16, 32 are going to be all of the factors of this. Now this one's nice because we could divide by 2 and take it all the way down, and that works out. Sometimes you might get something like 75, which we'll see in another example. And so you can go down so far, but then you also have to think, well, not only is it going to be the 5 and the whatever 25, it's also going to have different numbers. So you're going to have other things besides just going down that one side. You're going to have to go on all kinds of different directions. And then we have our a sub n is just 1, so luckily we don't have to worry about that. So what we have basically is going to be plus or minus, and then we can start at either end. We can go from the bottom up or the top down, so plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 4 over 1, plus or minus 8 over 1, plus or minus 16 over 1, and plus or minus 32 over 1. So again, 2, 4, 6, 8, 10, 12 different possible zeros we have here. And so that's a lot of things to actually have to do synthetic division on, or even the other way, you can plug in values and plug in 1 into this equation and see if we get 0 for an answer. Or you can plug in minus 1 and see if you get 0 for an answer. And either case, the division or the plugging in values will tell us if we have actual 0 factor. And so that's what we have here. So when we determine the actual zeros from a list of all of them, all 12 of them, there's basically two methods we use. The first one, basically we evaluate each f of p over q to see if that value equals 0. And if it does, then that's going to be a 0 or a factor, depending on how you want to write it out. As a factor is going to be something like now where'd my pen go? There it is. It's going to be something like x minus 2, whereas the 0 is x is equal to 2. So depending on which way you want to look at it, it's a factor or it's a 0. And so that's going to be that way. So you just plug in all the values and then get 0 for an answer, then that's a factor.
So if the last number is 0, like you mean if there's no remainder, then it's a factor?
No, oh no, that's in synthetic division. I mean, for this one, you're plugging in values. So say we have f of x equals, I don't know, 2x squared plus 3, and we say one of our values is 3. We want to see, is that a 0? Well, then we plug it in and say 2 times 3 squared plus 3. Well, that's not equal to 0, so that's going to be not a factor. So when you actually plug in the f over p, what happens is if this equals 0 when you plug that in, then it's going to be a factor. Now, synthetic division, that's going to be the other way. So then you're going to have your 3, then you'll have your 2, and then if you're plugging all in, 0, and then 3. And if this last piece is a 0, then it's a factor. So it depends on what you do. If you do the first one, you plug in the value into your actual function, plug it into your calculator for each of the things, and then if you get a 0, then it is a factor. Or if you do the synthetic division, if you do all the way down and your last thing here is a 0, then it's a factor. If it's anything else, like in this case, it's not equal to 0, so that's not a factor. And so if we did this, all the way down, it's not going to be a factor either. So I couldn't come up with a good example where it would be a factor, but
How do
That's
you
gonna
decide which method to use? Like, does it matter?
it depends on what you feel like doing or what the question asks for. So if it says use, the method 1, or plug in p over q for f and solve it down and see if it's a 0, then you do it that way. But the most of the time, what we're going to do in this, what I'm going to do is do synthetic division, just because it's easier, because you don't have to worry about if you have an x to the 5th and you're taking 1/3 to the 5th minus 5 times 1/3 to the 4th and doing all that. Unless you have your calculator and you're doing it all by hand, it's going to be complicated. But when you do it with the synthetic division, it's a lot easier. So I'm going to most of the time do the second one, but sometimes you can do the first one as well. It depends on what works best for you, and also what the question asks for and how to do it. So
Gotcha. Thank you.
mhm. All right, so let's see here. So this one, we're supposed to use the rational zero theorem to find all possible zeros. And then we're actually supposed to find which one of those possible zeros is the real zero. All right. So what we do, again, we're going to have to do our plus or minus p over our q. And so here, p is 1, q is 1. So basically all we're looking at is plus or minus 1 over 1, or just plus or minus 1. And so we're just going to do synthetic division, and we're going to do one with a minus or plus 1, and then if need be, we'll do one with a negative 1. So 3, 2, 1, 0. So we have a 1, a minus 5, a 2, and a 1. So we work our way down. And again, if we have a 0 here, then we know it's a actual 0 as far as a factor. So that's give us a 1. 1 times 1 is 1. Minus 5 plus 1 is minus 4. 1 times that's going to be a minus 4. That's going to give us a minus 2. That's a minus 2. That's a minus 1. So no, that's not a factor. So 1 minus 5, 2, 1. Again, bring that down. That's a 1. And so 1 times that's going to be a negative 1. Add those, that's negative 6. Multiply that, that's positive 6. That's 8. That's going to be a negative 8. And that's going to give us a negative 7. So that's a no as well. Okay. And so when you get no's on all your possible zeros, then what we have is basically there's no real zeros. Okay. And we'll get to what other kinds of zeros are going to be, and basically they're going to be imaginaries. But in this case, once we get to the point here that the two possibilities plus or minus 1 don't work, then we just know there's no real zeros, and we don't actually have to do any work beyond that one. Okay, because they're asking for only the real zeros in this example. All right, so what happens? What if we do get complex zeros of a polynomial function, or how do we find them? That's going to be the key. Now we're going to use the fundamental theorem of algebra, and basically it says if, again, we have that big f of x, it's some polynomial, it has degree. Now this time it's going to be greater than 0, so we're not limiting it to n greater than or equal to 1. Then what we have, then f of x has to be at least one complex zero. And so if a is a non-zero real number, so if we put it into a factored form and we have our a here, it's going to be a non-zero real number, then f of x has n linear factors. So basically you're going to have a factor here, dot, 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 all the way to the factor c sub n. Okay, where c1, 2, all the way through n are complex numbers. And so basically what's going to happen is your f of x, whatever your degree is going to have that many different roots. It doesn't matter, what it is. If n is 5, there's going to be 5 different roots. And we also have to be sure to allow for your multiplicity. So you might have one root of 3 and another root's 2, so that would be your n of 5. Now, the key thing is complex numbers can be either real or imaginary. So sometimes you're going to have only real complex numbers. Sometimes you're going to have only imaginary numbers. And so basically you just have to work the problem, and when you get done you'll find out what you've got, if you've got real ones or you've got imaginary ones. Now the key is, if you have an imaginary one, if you think about when we were doing those earlier, when we multiplied them back out, if you had or if you're maybe rationalizing the denominator, if you had a plus 2i on the bottom, then to get rid of that I, because we don't want to have an I in the denominator, you had to multiply by the conjugate. And so that also works with zeros. What we're going to have is we're going to have complex conjugates. And so we have got a complex conjugate theorem says basically if you have a polynomial with real coefficients and it has a complex zero in the form a plus bi, then you're also going to have the complex conjugate a minus bi. It also has to be a zero. And this is basically necessary to get rid of the imaginary term, because if you have, say, your f of x and you factored it down into x minus 2 and then maybe an x plus, and then you have your a plus bi, well, the only way to get rid of that there is to multiply it by this. And so you're going to have an x plus a minus bi. Because what happens is if you don't, then you're going to end up with an I still in your term, and we don't want that. This should be a minus actually here too. And so if you don't do that, then you're going to have problems because, when you take the a times a is a squared, a times the minus bi is a minus abi, then you have a times a plus bi, the i's cancel in that case, and then when you have b I times a negative bi, that's going to be a minus b squared I squared. Remember, I squared is a minus 1, and so we get rid of all that altogether. So we're trying to get rid of all the i's, and so you always have to have complex conjugates. And really, you're always going to get that anyway, because to solve for the ones with I in them, you're going to use a quadratic formula, and it automatically gives you plus or minus whatever it is. And so you don't have to worry about that usually. All right, so another thing that's going to help us is called Descartes Rule of Signs. So basically, if you have your polynomial written in descending order, we can actually determine the number of possible positive and negative zeros using Descartes Rule of Signs. So if we have our long polynomial again, and it's a polynomial function, real coefficients, descending order, the number of positive real zeros is either going to be equal to the number of sign changes in our function here. So if it goes plus, 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 plus all the way through, and there's no sign change, that'll be 0 positive real numbers. Or if you just have one sign change, that's going to be 1 positive real number. Or if you have multiples, it's going to be that number less an even integer. So maybe you started and you found that there were 3 sign changes. You go down by an even number, we'll say 3 or 1. So, or it could be, 4 or 2 or 0. So depending on how many sign changes you have, if you have an even number, you just keep going down until you get to 0. If you have an odd number, you go down until you get to the 1. So depending on which way it is, you're going to go down that many. And we don't know how many it's going to be. It could be 4, it could be 2, it could be 0, it could be 3, or it could be 1, depending on what the graph actually looks like. But those are the possible choices. You shouldn't, if you have this one to start with, you shouldn't come up with a 3. So if you come up with 3, there's going to be an issue there. So it's going to only be evens or 0 if you have that one. And here, you shouldn't come up with 2 because you start with an odd. It's either going to be 3 or 1. Now the negative zeros is going to be equal to the number of sign changes when you plug in a negative x into your original function. So you plug in negative x, simplify that, and then you'll have your negatives in different places, and then you look at the number of sign changes there, and it works the same way. It's going to be that number or lower by an even integer. So, if you started with a 3, it could be a 3 or a 1. If you started with, say, a 4, then it'd be 4, a 2, or a 0. Okay, so let's kind of look at that. Actually, we'll look at it in a little bit. What we're going to do is we're going to kind of tie everything in and just kind of start finding complex numbers with real and imaginary and all kinds of different ones. We're just going to be basically just solving examples here. All right. So on this one, what we have is we need to look at our P's and Q's again. So plus or minus P over Q. Well, luckily, this sometimes they work out nice. It's just going to be either plus or minus 1. Okay. Now here, this is kind of a one that you can think about, logically and do, or we can use Descartes' rule of sign. So Descartes' rule of sign says how many changes do we have in sign? Well, guess what? There's no sign changes. So that means no positive real number is going to be a 0. And because of that, we can get rid of the positives. And what if we plug in a negative up there? Well, if we get a negative up there, f of negative x is negative x to the third plus x squared minus x plus 1. So we have one sign change here, one sign change here, one sign change there. So there's 3, or reduce it by an even number, 1 negative zeros. Okay. So we know we only have to worry about that negative. So we do that. And so we have a 1, a 1, a 1, and a 1. So we bring down our 1. That's going to give us a negative 1. That's going to give us 0. That'll give us 0. Add that, we get 1. Multiply that, you get negative 1. Add that, you get 0. So our factor then is x equals, better put 1 there, negative 1 is a 0. And what do we have left? Well, we have x squared, and then we have plus 1, because we have subtracted 1. That's going to be x squared plus 1. And so x squared plus 1 equals 0. If we solve that for x to get the other zeros, we'll subtract 1. So x squared equals a negative 1. Take the square root of both sides. And so we get plus or minus I in this case. So we have x is equal to 1 is a 0, x is equal to a negative I, and x is equal to a positive I. Notice the conjugates. And that's what we would expect. If you have one imaginary number, you should have the conjugate of it. And when you take plus or minus the square root, then you get both plus and minus the I. So we ended up with 3 zeros, but we only ended up with the 1 negative 0 that was real. So this is negative real zeros. And then we had the 2 imaginary zeros. Okay. So this one, we should get 3, and we got 3. We got 1, 2, 3. One of them that's real, 2 imaginary. Okay. All right, with this one, it's going to be a little more difficult because our P and our Q, again, our P is going to be a lot bigger. We have 75, so we have to break it down. And so 75, we can have 5 and 15. That's going to be 3 and 5. But, you know, we could also have 3 and 25. Of course, 1 and 75. So we have all these different possibilities here. And so our plus or minus P over Q, luckily Q is just 1, so we just have to take all those. Plus or minus 1 over 1. Then we have also a 3, so plus or minus 3 over 1. Then we've got a 5, so we can do plus or minus 5 over 1. And then we've got a 15, so plus or minus 15 over 1. And we've got a 25 over 1. And then we've got our 75, which is the original number. So we've got 2, 4, 6, 8, 10, 12 possible values here that we can look through. All right, so what do we know about sign changes? Well, we have 1 here. So that's going to be 1 positive real. And then if we plug in negatives, can we get that? Well, that's going to give us x to the 4th minus 2x to the 3rd plus 22x squared minus 50x minus 75. So that's going to be 1, 2, 3, or 1 negative real. So it looks like we're going to have more possibilities of negatives. Maybe not, because it could still be like on the last one, you just have the 1 is what it actually is. And so what I'm going to do is I'm just going to start from the left and work my way up, because it's just going to be easier that way. Let's start with 1, because we know there's going to be at least 1 positive real. So let's start with 1. So we have 1, 2, 22, 50, and minus 75. All right, so 1. 1 times 1 is 1. 2 plus 1 is 3. 1 times 3 is 3. That's going to give us 25. That's going to give us 25. That's going to give us 75. That'll give us 75, and that's 0. So that being 0 says that x equals 1 is a factor, or is a 0. Okay, so we've got one of our zeros. Now, with this one, we could go ahead and do all the p's and q's again, but guess what? It's the same number as this one is, and so basically it's going to be our same list of p's and q's. And so since I know I only have one positive real, I'm going to switch to negatives now. So now I'll start at the lowest, -1. And so then I'll have the 1, the 2, the 22, 50, minus 75. So I'll bring down the 1, and then I have 1 times that. It's going to be -1. 2 minus 1 is 1. That's going to be a -1. 22 minus 1 is going to be 21. And then that's going to be a minus 21. And that's going to be what? 29. And so that's going to give me a minus 29. And so I'm just going to say, no, that's not going to be a factor. So we don't have to worry about that one. So now we go to the next one that's negative. So the next one is 3. So -3. So I have 1, 2, 22, 50, -75. So we have 3 times that, it's -3. That's going to be -1. It's going to be a +3. It's going to give me 25. That's going to give me a -75. So that's going to give me a -25. That's going to give me a +75. That's 0. So that one is a factor as well. So what do we have now? We have x is -3 is a 0 as well. And so what do we have here? That was x to the 4, so that was then x to the, oops, you know what I did? I have my 2 factors, but I didn't use those numbers there. So I kind of made things a little more complicated than I should have. This should have actually gone into the 1, the 3, the 25, and the 75, because I should have used the 1 here. I shouldn't have gone back to the original. So we will do that now. Sometimes things don't work out how I plan. So that's going to be 0.
Is it correct if you do it either way, though?
Yeah, it's correct. But see, when you get, if you do it this, what I'm doing now, that'll give me the last thing. So I'll have, you know, the x minus 1, I'll have x plus 3. And then if I would have had that, that would have told me what my last remaining x squared. And then I could maybe factor that really easy. And so doing it with the previous one, just make sure you go down one step, and so it's easier to factor. Because what I have now is, now I've got this whole thing, and now I'd have to factor that again. And but the key is my other factor is right here, so it's not going to help me getting this number, because that's going to be, you know, x cubed, x squared, x, and then the number. And factoring that, I need to first take out that 1 to get it to a lower number of an x squared, and so on, so then I can get a trinomial that I can hopefully factor or use the quadratic formula for. So that was my bad there. So okay, so that's 25, and then that's a minus 75, and then that's 0. So then that's when I get x squared plus 25 equals 0. And so then I can subtract 25. So x squared equals a minus 25. And so to simplify that, I would take the plus and minus square root of both sides. And so that gives me plus or minus 5i. And I see at this point, I wouldn't be able to get my plus or minus 5i, because I'd have to first divide it by the 1 again. And so really, this whole thing was just to say, yep, that's a 0. And if I was only looking for zeros, I'm done. But the key was I was really looking for all the zeros, so I needed to get to the easier one where I got down to the final thing here. And so, as usual, we have the first one, 5i, but we also have its conjugate, a negative 5i. So now we've got our 4 roots, which is what we need because we have to have n is 4, so we have to have 4 roots. And we have 1 positive, 1 negative, and then 2 imaginary. Okay. All right, so any questions on that before I go on? And again, this here whole thing shouldn't have even been done. That was a mistake. It should have gone from here, and this one either it should have gone from here up those numbers up there, but either way it didn't work for -1, so no matter what. But I should have then put it over here and gone to the one where I got the 1 0 25 0. So all right, so that's that one. Let's go ahead and see what else. Okay, so this one is using Descartes Rule of Signs, but we've been kind of doing that already. We've been seeing, 3 or 1 negatives, 1 positive, and that just helps us really to kind of reduce our workload is really what it's going to end up doing. So if we think about this, all it's asking for here, I guess, is find the maximum number of positive and negatives. It doesn't actually tell us to solve for the zeros. But what it wants us to do is graph to verify the numbers of zeros with a calculator. So we're just going to use a calculator to find those. But first, we're going to find the zeros. So we have 1 change there, 1 change there, 1 change there, and 1 change there. So there's going to be either 4 or 2 or 0 positive zeros. Now if we find f of negative x, that's going to still give us 2x to the fourth. Now we'll have plus 10x to the third plus 11x squared. Now that's going to change to a plus 15x and then plus 12. And so guess what? There's no changes there. So that means there's 0 negative zeros. Okay. And so what now I need to do is make sure I have this written down, so then we can go to the calculator. And let's go to our TI. So now what we have is we have a 2x to the fourth, and then minus 10x cubed, and then plus 11x squared. Oops, where'd my plus go? And then minus 15x, and then plus 12. And I don't know what the window is going to be, but let's graph it and see if we're anywhere close. And let's see, this was x to the fourth, so it's going to be both going up. So this looks like that. We don't care about what it goes. It can go down here forever, and it's going to go up to the left and go up to the right. But it crosses at a positive number here and a positive number here. So that says there's going to be 2 positive zeros here. So one of them is going to be, between there and there. So it's probably at a 1. And then we go all the way down, come up the other side. Hopefully it'll, okay, so it's going to be right around 4. So 1 and 4 should be our 2 zeros. And so that's what we expected. We needed to have either 4, 2, or 0. And the 2 was actually how many we had. And so then when we did it, all those calculations before, we could do the p's over the q's, and we're going to come up with the 2 that work. It's going to be the 1 and the 4 that actually work. Okay. So all it really asks on this one is just to list the number of possibles and then graph it with the calculator to see what the actual number is, and it was actually just number 2. All right, so then we have application problems as always. And so with this, we're looking for a box. And it says the length is 3 times the height, and the height is 1 inch less than the width, and our volume is 108. So what all do we know? Well, let's kind of write somewhere over here. volume is equal to length times width times height. So let's let h equal the height. And then the length is 3 times the height. So length equals 3 times h. And then it says the height is 1 inch less than the width. So we're going to have width is equal to the height plus 1. Because it's going to be, said the height is 1 less than the width. So if we add 1 to it, that's what our width would be equal to. So now we've got h, we've got L, and we've got W. So basically what we're going to plug in is we're going to plug in h, 3h, and h plus 1. That way we have it all in terms of one variable, and so then we'll have some cubic value. And so v of, let's call it, I guess, h is going to be equal to h times 3h times h plus 1. Now we have to multiply that, so that's going to give us 3h squared times h plus 1, and that's going to be 3h cubed plus 3h squared. And then what do we know about it? Well, that's equal to 108. Okay, so if that equals 108, now we have our equation. And so most of our polynomials, we have all the things on one side. So if we subtract our 108, we have 3h cubed plus 3h squared minus 108 equals 0. Now, do I notice anything? I notice 8 plus 1 is 9, so this is divisible by 3. All of them have 3 in it. So if I divide by 3, then I can reduce what I have. So that's going to give us h cubed plus h squared minus 3, 6 equals 0. And so now I've got this in terms of the thing where we can find our p's and our q's and start solving and things like that. And so first, let's think about our Descartes theorem and signs. So if we move across here, we're going to have to add in a 0. So let's do this up here. So let's say v of h is equal to h cubed plus h squared plus 0h minus 36, and then we already did that. We don't need the minus there now because we put it equal to the volume. And then we can also find v of a negative h, and so that's going to be negative h cubed plus h squared, and then we can have that to be minus 0h and then minus 36. And so we go across, here we have 1 positive, and we have, looks like 1 negative. But what do we know about volumes and lengths and widths and measurements? We better only use positive numbers. So when we get our p's over q's, we only have to worry about the positive ones because, even though it says we're going to have one of each, when we start finding the height and the width and the length, those had better be all positive numbers. So that's what we have to think about there. So we're only worried about positives. And so let's do our plus and minus p and q. So what do we have? We have a 36. So we can do 2 and an 18 and a 2 and a 9 and then a 3 and a 3. And then we'll also have a 1. And then we'll have, we can do a 4 and a 9. And then we can also do, it looks like, a 12 and a 3. Anything else we can multiply and get there? So
6 and 6, right?
Oh yeah, 6 and 6. Yeah, darn, even more. And then 6 and 6. Yeah, so we've got a lot of p over q's, and luckily q is 1. So our plus or minus p over q is going to be. And now remember, we only have to have our positives, so we can just put our ones and only positive ones. So we can have 1, 2, 3, 4, 6, and we got 9, and 12, and 18, and I guess after that 36. So 1, 2, 3, 4, 5, 6, 7, 8, 9. which is a lot of them, or we could have 18 if we also had to do the negatives. So luckily we only have to do the positives. And I think when I've looked at all of problems I've ever done over the years, I always just start with the smallest and work my way up, and it usually ends up working best. And sometimes you're going to end up with fractions, and do the fractions first. You know, you might think, oh, those are going to be hard, but a lot of times those will actually cancel out and give you it's a factor before, you know, any of the other numbers. So you might have also, maybe you had a third and a half and a quarter. Do those before you do one, because sometimes one of those will be a term or a zero, and then you don't have to do many more, because then you can just directly factor the trinomial after that, the quadratic, and you don't have to worry about all these other terms to divide. So I would do fractions first and then go up from there on the numbers as far as how I would do the divisions. So let's do 1. And so we had, now we can use our 1, 1, 0 minus 36. 1, 1, 0 minus 36. Bring down our 1. That's 1, that's 2, that's 2, that's 2, that's 2, that's a no. I'm not even going to add them. Just not going to be 0. So next one, 2. So that's a 1, a 1, a 0, a minus 36. 1, that's a 2, that's a 3, that's a 6, that's a 6, that's a 6. Again, no. So next is 3. So we have a 1, a 1, a 0, a minus 36. That's a 1, then we get a 3, that's a 4, that's a 12, that's a 12, that's a 36, that's a 0. Yay! So x is 3 is one of my zeros. Is a 0. And then here I've got x squared plus 4x plus 12. And so let's see, can we factor that? So x to 6 and 2, maybe x plus, nope, it's going to be, we can't get that one. We're going to have to, oh, wait a minute. We're looking for a volume of a box. We don't even have to solve that, because that's going to end up being a imaginary number. It's not going to actually work, I don't think. And so that's x is equal to 3, or in this case, it was our h. So our height is equal to 3 inches. And then our length is equal to 3 times h, so that's going to be 9 inches. And our width is going to be equal to 3 plus 1, or 4 inches. And so if we think about that, you know, 4 times 9 is 36, times 3 is 108, which is what we got up here. And so those are the dimensions of the box. Okay. So actually, we didn't even care about that, because again, you're going to have to use a quadratic formula to get that, and then that's going to give you an imaginary number. All right, so that's one application. The other one is going to be just a different formula. It's going to be the right circular cylinder. And so what do we know about the volume of the cylinder? That's going to be equal to pi r squared times h. So basically the area of the circle times the height of our cylinder. And so what do we know? Well, let's say we have the radius is 3 inches more than the height. That's all we know, plus the total volume. So if we say h is equal to the height, then the radius is 3 more than that. So it's going to be height plus 3. And so now we know everything. We know h and we know radius. So if we go ahead and plug in our 16, we can do that on the left side. 16 pi equals pi times r, which is h plus 3 squared times h. Okay. Now we simplify. Well, first thing I notice, I can cancel pi on both sides, because if I divide by pi, that gets rid of it. And so that simplifies things quite a bit. Now I have 16 equals. Now if I square that, that's h squared plus 6h plus 9. That's all still times h. And so 16 equals h cubed plus 6h squared plus 9h. And then I'll subtract 16 from both sides. And so I've got h cubed plus 6h squared plus 9h minus 16 equals 0. And we've got also one positive 0 here possible, and using our Descartes theorem. And again, we're going to have a positive h anyway, so that's good. We don't care how many negatives there are or how many imaginaries there are. And so now what we have to do is figure out our p's and our q's. So our factors of 16, that's going to be 2 and 8, 2 and 4, 2 and 2, 2 and 1. So it should be 1, 2, 4, 8, and 16. And so plus p over q, we don't care about the negatives. That's going to be 1, 2, 4, 8, 16. Now again, I'm going to start with the 1 and work my way over. So 1 and 2, and we have a 1, we have a 6, we have a 9, and a negative 16. So do this, we have 1, so 1 times 1 is 1. 6 plus 1 is 7, that's 7. That's 16, 1 times that's 16, that's 0. Yay, we got done with the first one. So our height is equal to 1, and we're in inches again. Well, I guess we just need inch, not inches. And then our radius is going to be 1 plus 3 or 4 inches. So if we take and plug that in, our R4 squared is 16 times h is 1, and that's 16 pi, and that's what our volume was 16 pi. So that does appear to be the correct answer there. Okay. And so that's all I'm going to do for in class. I'm going to make up a whole bunch more examples on another sample video of exercises that'll hopefully help you do different types of problems or even ones that are just more complex. And I guess have a great Easter weekend.